All right, so welcome to the second of the 3 review sessions. So the goal is to spend about 50 minutes to an hour just talking about the key ideas in Calculus 2. This is a continuation of the key ideas in Calculus 1 and will be followed by the key ideas in Calculus 3. So what is really motivating us? Well, calculus has 2 main branches. In Calc 1, we mostly look at the derivative. And the derivative is defined as, given some function f prime of x is the limit as h goes to 0 of f of x plus h minus f of x over h. Sometimes we write it as f prime of a is the limit as x goes to a of f of x minus f of a over x minus a. Another way is f prime of a is the limit as x goes to a of f of x minus f of a minus f prime of a x minus a over x minus a. And it turns out the last is the one that generalizes best. And what's really going on here is we can view f of a plus f prime of a x minus a as estimating where we will be. So this estimates where we will be. So f of a is our instantaneous location. It's where we are at time a. F prime of a is our instantaneous speed. X minus a is elapsed time. So if I wanted to try to estimate where I would be, I look at where am I, how fast am I moving, and how long have I traveled. And so Calculus 1 talks a lot about that, and we have lots of rules to find derivatives. What do we do in Calculus 2? So in Calc 2, Calc 1, I give you a curve like this, and maybe this is time, this is distance, and then we have some plot over here. So here is y equals f of x. So this gives you your distance as a function of time. If I want to estimate speed, what I could do is I could look at some point A and some point A plus h, and look and see, let me change where the points are. So here's A plus h. And what I can do is I can try to estimate. So the elapsed time, the change in time is h. And I can look and see how much have we moved. And that'll be the change in the distance. And then what we can do is we can estimate, the average speed is delta d over delta t. Take the limit as the change in time goes to 0. And in the limit, what we'll get is we'll get the tangent line. And the slope of the tangent line will be the speed at the point. In Calc 2, what we do is instead of trying to figure out how fast we're changing, we try to figure out how far we've gone. So now over here is maybe here's time, and now over here is speed. And so if I give you some curve now, I want to look at what is the area under the curve. So here's A, here's B, and I'm asking what is the area under the curve from A to B? And if I know what my speed is, the hope is that I should then be able to figure out this area. So we start off with some simple cases. Always start with a simple case and try to build up. So the simplest thing we could consider is here's time, here's speed. What's the simplest speed function you can think of? Simplest function you can think of. Oh, y equals x is complicated. There's something even simpler than y equals x. Y equals 2, y equals 3, y equals some constant. So we take, f of x equals some constant c. So we're traveling at constant speed. And so if I want to find the area under the curve from A to B, the area is equal to c times b minus a, as we have a rectangle. Okay, not really that interesting because it's very simple. The next thing is, as you suggested, let's take something a little bit more complicated. And now let's take as the speed, oops, let's take as the speed f of x equals x. And so now if we want to find out, let's take a to be at 0, b sometime over here, we want to figure out how far have we traveled. Well, this is a triangle. We can figure out the area of a triangle. Its area is 1/2 base times height. So here it's going to be 1/2 b times the height. And since y equals x, that's going to just be b. So it would be 1/2 b squared in this special case. And if you think about it, does this seem reasonable? So my speed is constantly increasing, but it's increasing in a linear way. Let's try to zoom in and see what's going on. If I gave you, here's time, here's speed. Imagine I gave you some kind of nice step function like this for speed. We have lots of moments where your speed is constant, you instantaneously increase, and then you're constant, then you instantaneously. Well, if I give you something like this, then to figure out, the area under the curve, that's not going to be so bad. So the idea is that we can use that to find the area under the curve. And if you think about units, speed times time, well, speed would be in meters per second times time in seconds. That will give you meters. So that should give you the distance traveled. So if we look at what's going on in general, so here's speed, here's time. If I give you some general curve, the hope is that, yes, we should be able to figure out the area under the curve, and that should be the distance traveled. So the question is, how do we figure out the area under the curve? So this is the curve y equals f of x. And so we use the following notation. So this is the integral sign. It means a to b f of x dx is the area under y equals f of x from x equals a to x equals b. So this is just notation at this point. We're using this to denote the area under the curve. We can approximate the area under the curve. And we can approximate it with lower and upper sum approximations. So how do we do that? Well, let's say, I have my curve, and let's say go from 0 to 1, and I break it up into lots of different points. And here maybe is xk. And so, just zooming in, here's xk, which will be k over n. Here is xk plus 1, which would be k plus 1 over n. We're breaking it up into n equal spots. And so I have my function, I zoom in, maybe something like this. And what I want to do is I want to estimate the area under this curve. And what I can do is I can look and see where's the function smallest. And let's say it's smallest at some point, let's call it L sub k for the lowest value. And I can look and see where is it largest. Let's call that U, the upper. And so the idea is the area in the kth segment is going to be less than equal to f of uk times 1 over n, the rectangle with height f of uk and base 1 over n. And it's going to be greater than or equal to the lower value. And then we just sum over k. And so we get the lowest sum with n partitions is the sum k goes from 0 to n minus 1, flk 1 over n, less than equal to area, less than equal to the sum k goes from 0 to n minus 1, fuk 1 over n, which is the upper sum. And then, this is just meant to be a quick introduction. We have to show that these sums converge. Well, we know that true area is always going to be at least the lowest sum and at most the upper sum. So if the upper and the lower sum converge, the only thing they can converge to is the true area. If it converged to something that was less than the true area, then that would, contradict that the upper sum is always greater than or equal to the area. So if they converge, it has to converge to the true area. So we can numerically approximate the area. That's great. Can we actually come up with a nice formula? And it turns out if our functions are nice, we can. And this is the fundamental theorem of calculus. And so if f is continuous and bounded on AB, so that means, for instance, it's at most 5 in absolute value at 20 or 30, whatever. And big F is any antiderivative of little f. That means the derivative of big F is little f. And this is why we use this as notation. So when you see big F, you should immediately be thinking, okay, it's related to little f. Then the area under the curve from A to B of f of x dx is big F of B minus big F of A. So this would be the fundamental definition of calculus if I didn't say that this was area. I could define this if I wanted to be f of b minus f of a. If I define it to be that, then it's not that big of a deal. The important part is that this is the area under y equals f of x. And so the fundamental theorem of calculus gives us a way to compute this. So we can check. And again, in class we would go through the checks carefully. Let's check when f of x equals x. So if we take our example, let's go from 0 to b as we did before. So if f of x equals x, we want a function whose derivative is little x. So that's 1/2 x squared. And you can check and see if you take the derivative, you get back x. Now, one thing you have to be careful about is there's infinitely many functions that have the same derivative, because I can add any constant and the derivative of a constant is 0. But if you look at the fundamental theorem of calculus, we look at big F of B minus big F of A. So if I add a constant to big F, I add it to the value f of b, and I add it to the value f of a, and then I subtract, so it cancels. If you've done physics and you've done potential energy, all that matters is the change in potential energy. The value of the potential energy doesn't matter. It just matters about the change. And so here, if I then look at big F of b minus big F of 0, that'd be 1/2 b squared minus 0 is 1/2 b squared, exactly as before. As a more interesting check, we could do is we could take f of x is x squared from 0 to b, and then try to find the area under the parabola. Now, if we do that, the problem is we don't know a formula for the area under the parabola. Squares, rectangles, triangles, I know. Well, we could go back and look at the definition of the lower sums and the upper sums. And it turns out we could calculate those sums and see that it does converge to the area. So we can check the fundamental theorem of calculus in a lot of different settings. So what this tells us is we can use calculus to find areas. Why do we care about areas? So areas are often probabilities. And that's one of the reasons why we care so much about finding out this stuff. So for example, we say x is a random variable with density p of x if the following holds. P of x is greater than or equal to 0. The integral from minus infinity to infinity of p of x dx equals 1. And the probability that x takes on a value between a and b is just the area under the curve from a to b. So if we can find functions that are non-negative and integrate to 1, we can associate these to random variables. We can use these to model things. We can use these to talk about the odds of things happening. It then comes down to, can we actually do the integrals? So there's a huge difference between Calc 2 and Calc 3. Calc 2, it's very easy for me to come up with functions that you can't find the antiderivative of. Calc 1, I can't come up with any function that you can't differentiate. If you just keep using the rules, you will get the derivative. So for example, if I give you f of x is 3x squared e to the x cosine e to the x plus 2, this looks painful. Well, what I could do is I could say, well, look, let me set this up as a product rule, and I'll group it like this. And so I'll call this a of x, I'll call this b of x. F prime of x is going to be a prime of x, b of x, plus a of x, b prime of x. A of x is 3x squared e to the x. A prime of x, okay, I would use the product rule for this. And so if I use the product rule for that, I'd have the derivative. And again, you can always decide how many steps do you want to put in. I would have the derivative of 3x squared. So it's going to be 6x times e to the x plus 3x squared times e to the x. B of x is just going to be cosine e to the x plus 2. Whenever you hear of, you should be thinking chain rule. So I can write b prime as I've got maybe some function c of d of x. And I want to take the derivative of that. So that would be c prime of d of x times d prime of x. And I can just use the chain rule to figure that out and then put all the pieces together. It may not be fun, but I can't stump you. If I give you, f of x equals e to the x squared, it turns out there's no nice function that's the antiderivative, that has the derivative of e to the x squared. So what we can do is we can try to come up with a table. So here's f of x, here's its antiderivative big F of x, and over here, here's f prime of x. And so if I give you the function x to the r, its derivative is r x to the r minus 1. Its antiderivative is going to be 1 over r plus 1 x to the r plus 1 if r is not negative 1. And then it turns out to be the natural log of x if r equals negative 1. And the derivative of the natural log is 1 over. So you have to be a little bit careful. These have to be proved rigorously. We can look at other functions, e to the x. Well, this is actually one of the beautiful ones. Its antiderivative is e to the x, and its derivative is e to the x. If I give you cosine of x, its derivative is minus sine of x, and its antiderivative is sine of x. And if I give you sine of x, its derivative is cosine of x, and its antiderivative is negative cosine of x. And it turns out that the derivatives of sine and cosine are related to the exponential function. We talked about that in the Calc 1 review. So the question is, how do we find antiderivatives? So part of it is just you create a table. And once you find one, then you record it and you remember it. It turns out, integration rules come from derivative rules. So for example, if I give you the integral of f of x plus g of x dx, so we have to be careful about what do we mean. Are we talking about a definite integral of the area under the curve from, say, a to b? Or are we talking about finding the function that has this as its derivative? And so if we have just the general what function has this as its derivative, we have this plus c that we have to remember. Well, if I have multiple constants that are plus c, I can just combine them all as to my new constant at the end. So this is just going to be the integral of f of x dx plus the integral g of x dx. The integral of a sum is the sum of the integrals. The next one is the integral of c times f of x dx is just c times the integral of f of x dx. So think about it as if I've tripled my speed, then in the same amount of time, I've tripled how far I've gone. So these have natural interpretations. If instead of doing the sum, I did a minus, it wouldn't be a big deal. So if I give you, find the integral from 3 to 4 of 2x cubed minus 7x plus 1 dx, this would be the same as the integral from 3 to 4 of 2x cubed dx minus the integral from 3 to 4 of 7x dx plus the integral from 3 to 4 of 1 dx. And then that would be the same as 2 integral from 3 to 4 of x cubed dx minus 7 integral from 3 to 4 of x dx plus the integral from 3 to 4 of 1 dx. And then this becomes 2 times x to the 4th over 4 evaluated at 3 and 4 minus 7 x squared over 2 evaluated, and this is just notation. The vertical line means evaluated at 4 and then subtract off the value at 3, and then plus x evaluated at 3 and 4. So again, we break a complicated problem into a lot of simpler problems. Okay, so we have the product rule and the quotient rule and the chain rule still to come. So each of these has to give us something for integration. If you ever became the supreme deity and could choose how to create the world, almost surely you would not initially choose to say the derivative of a product is the derivative of the first times the second plus the first times the derivative of the second. You would say the derivative of a product is the product of the derivatives. The derivative of a sum is the sum of the derivative. But no, it doesn't work that way. And so because of that, we have a more complicated product rule for integration. So we start with, if I give you f of x times g of x, and I ask for its derivative, it's f prime of x g of x plus f of x g prime of x. All right, well, rather than using f's and g's, we often use the letters u and v. And so this is what's called integration by parts. And so I will switch this, and we'll say integration by parts. And if I give you the function u of x times v of x and ask for its derivative, that's going to be u prime of x v of x plus u of x v prime of x. So that means u prime of x v of x equals u of x v of x prime minus wait, I think I'll fix this. Minus u of x v prime of x. Except I actually want it the other way, so I want to switch which one I move to the other side. So I'm going to just quickly switch that, and I'm going to do it so it's u of x v prime of x over here, and u prime of x v of x. I'm going to switch which one I move over. Well, if I integrate both sides from, say, a to b, u of x v prime of x dx, that's going to be the integral from a to b of u of x v of x prime dx minus the integral from a to b of u prime of x v of x dx. Now, if you look at the first integral, this is the simplest problem I can legitimately ask you. I'm looking for a function who, when I take its derivative is the derivative of the function u of x v of x. So what function has derivative equal to the derivative of u of x v of x? It's just the function u of x v of x. So this piece here is just going to be u of x v of x evaluated at 2 endpoints. And if we use the notation v prime of x, if we think of this as dv dx times dx, and we think of this as du dx, the way we often view this is the integral from a to b of u dv equals uv at ab minus the integral from a to b of v du. This is how we really come up with integration by parts. It comes from the product rule and just choosing which thing we put on the other side. So let's do an example to see what's going on. So for example, let's say I give you, we want to integrate from 1 to 3 of x e to the x dx. And so when we look at this, we don't immediately see what function has derivative x e to the x. So what we want to do is we want to say, okay, we need to choose what's our function u of x, what's our function v of x, and then we'll get our function, du, and sorry, this was like dv, and then we'll have our function v. So what should u of x be? Well, we really have two choices, x or e to the x. For more complicated ones, you have more things to look at. Here, you have really only two things. If your choice doesn't work, try the other. Well, we're going to take the derivative if we make u of x equal x, and that will go from having a polynomial of x to a polynomial of smaller degree. That's making things easier. If we had u of x equal e to the x and dv equals x, then v would become x squared over 2. We'd be making it more complicated. So it seems reasonable to try u of x equals x. dv is going to just be e to the x dx. So then v of x would just be e to the x, and du would just be dx. And again, if you want to think of it the longer way, du dx would just be equal to 1. And so if we multiply by dx, it gives du equals dx. So this is supposed to equal the integral of v du from 1 to 3. I'm sorry, forgot the boundary term. It's supposed to equal u of x, v of x at 1 and 3 minus the integral from 1 to 3 of v du. And so when we substitute, u of x, v of x is going to be x e to the x at 1 and 3 minus the integral from 1 to 3 v du. V is e to the x, du is just dx, so it's just e to the x dx. So this is going to be 3e cubed minus 1e to the first. And then the integral of e to the x is just e to the x, evaluated 1 and 3. So it's just 3e cubed minus e cubed minus e. And if we look at that, okay, we have 3e cubed minus e cubed is just 2e cubed. The minus e's cancel. If I've done things correctly, we should just get 2e cubed. Now I might have dropped something wrong, but this is u substitution. I'm sorry, this is integration by parts. And the hard part is just figuring out which substitutions do you want to make. If I give you something that's a little bit harder, it can become a bit more of a challenge. So if I give you, I'll leave it like that. Let's move on to u substitution. So for u substitution, this is really coming from the chain rule. And so what's going on is, if I give you f of g of x, and I ask for its derivative, it's f prime at g of x times g prime of x. Well, then that means if I integrate from a to b of f of g of x prime dx, that should be the same as integrating from a to b of f prime g of x g prime of x dx. All right, what function has derivative equal to the derivative of the function f of g of x? Well, this is a function f of g of x. So this integral over here is just going to be f of g of x evaluated at a and b. And so if I happen to be fortunate enough to have something of the form f prime at g of x times g prime of x, well, then I immediately know that the integral is just f of g of x at those points. So what we frequently do is, it's called u substitution. We let u equal g of x. And so then g prime of x dx would be du, or du dx is g prime of x. So multiplying through gives us, du equals g prime of x dx. We're just playing a little fast and loose with the math. But this is essentially what u substitution is we replace g of x with u. Now we have to be a little careful when we do u substitution. So as an example, let's consider the integral from -2 to 2 of e, let's do x e to the x squared dx. When you look at this, do you have any intuition as to what the answer should be? Okay, so if you plot this, what you would notice is this is an odd function. The value of negative x is equal to the negative the value of positive x. So maybe it looks, something like this. So if you know that it's an odd function, what should the area be? It should balance out. So the positive stuff you have over here should be canceled with the negative stuff here. So we expect 0. Let's do it by u substitution. So when we look at this, we think, oh, we have e to the x squared. If we let u equal x squared, then du would be 2x dx. Or x dx is 1/2 du. Well, we actually have an x dx. When x equals -2, what does u equal? 4. And when x equals 2, what does u equal? 4. So if we do this, our integral would equal the integral u goes from 4 to 4. E to the x squared becomes e to the u. X dx becomes 1/2 du. So this is the same as 1/2 the integral from 4 to 4 of e to the u du. Okay, I know the integral of e to the u is just e to the u, but in some sense, there's really no need of even doing this because I'm evaluating it. Oops, it's 4, not -4. I'm evaluating it at the same point. So it's just 0. So what went wrong? What went wrong was my change of variables. And this is a subtle point for u substitution. You need a one-to-one transformation. For each value of x, there's one value of u. For each value of u, there's one value of x. Here, when I look at what's going on, just get rid of there. So when I look at what's going on, so here's my plot, u equals x squared. So when I plot it, if you give me a value of x, okay, good, it gives me a value of u. But if you give me a value of u, there's 2 different values of x that correspond to it. And so what we really need to do is if we're integrating from -2 to 2 of x e to the x dx, is break this up as -2 to 0 x e to the x dx plus the integral from 0 to 2 x e to the x dx. Now for this problem, we don't need to do this because the integral is just going to be 0. But if instead I gave you, say, the integral from -2 to 2 of x squared e to the x dx, then that would be a difference. These were x squared, sorry. Then this would be a very different story because now we don't expect it to be 0. So for the most part, u substitution is not too bad. It's just trying to figure out that what you have can be written in the form f prime of g of x times g of x. So for example, let's say I give you the integral from 0 to pi of sine of x cosine of x dx. One way to look at this is to say, well, we know the derivative of sine of x is cosine of x. So if I let u equal sine of x, du dx is cosine of x, therefore du is going to be cosine x dx. Okay, when x equals 0, if u equals sine of x, what does u equal? So sine of 0 is, so if it's been a while, what you can always do is draw the unit circle. And so here's the unit circle. And so here's the point 1, 0. Here's the point 0, 1. Here's the point negative 1, 0. Here's the point 0, negative 1. And so if I give you a point over here at an angle of theta, this is cosine theta, sine theta. And so we see when the angle is 0, the sine, because so here, the vertical part here, this is the sine of theta, and over here, that's the cosine of theta. So when x equals 0, the sine of 0 is just going to be 0. When x equals pi, let's do pi halves. So when x equals pi halves, then the sine of pi halves is 1. So our integral is going to equal the integral u goes from 0 to 1. And I like to write u equals, so I remind myself I've now switched to a u integration. And then sine of x, that becomes u. Cosine x dx becomes du. Okay, well, that's just going to be 1/2 u squared at 0 and 1. So it's just 1/2. So this is how we can do it by using u substitution. We could, of course, look at this another way. So we have the integral from 0 to pi halves of sine of x cosine x dx. If you remember your trigonometry, which is always a dangerous thing to ask, it's 1/2 2 sine x cosine x dx. So 2 sine x cosine x, we talked about that last time, that's just going to be the sine of 2x dx. So now, if f of x is the sine of 2x, I want a function whose derivative is sine. Let's see, the derivative of cosine is minus sine. So I might try, maybe it's going to be minus cosine of 2x. And when I take the derivative of minus cosine of, I use the chain rule, I get minus from the minus outside. Derivative of cosine is going to be minus sine, with the minuses reinforce. So I'll have a sine of 2x. Oh, but then I have the derivative of sine of, the derivative of 2x, which gives me an extra factor of 2. And so I see, oh, okay, so if I divide that by 2, it should work. And so now what I would get is that this is just going to be 1/2 times negative 1/2 cosine 2x, all at 0 and pi halves. Let's see, the cosine, when I put in pi halves, the cosine of 2 times pi halves becomes the cosine of pi. Cosine of pi is negative 1. So it's going to be negative 1/4. And then the first one is going to be negative 1. And then when I put in 0, the cosine of 0 is 1. So I'm going to have a minus 1. And it's going to give me minus 1/2 just as before. So we could do this without doing u substitution by just using trig identities. What's interesting is when we do it this way, we get the antiderivative is minus 1/4 cosine 2x. When we do it this way, we're essentially getting the antiderivative is going to be like a 1/2 sine squared. And this tells us that you can have two different trig expressions that are equal but will look different. And this is especially painful in integration because you have this plus c. So the two functions don't have to be the same. They just have to differ by a constant. So depending on how you choose to do it, different things can come. So this is u substitution. This is integration by parts. The next one is we have trig substitution. I'll probably skip a partial fraction. So trig substitution. So if I give you sine squared x plus cosine squared x equals 1. This is the well-known Pythagorean formula. We know this, we love this. This is very useful. So if I want to integrate things and I see things like a sine squared or a cosine squared, this is often very helpful. So how could we use this? Well, let's do a problem that's worth doing. And in some sense, this is going to be cheating a little bit, because to prove that the derivative of sine is cosine, the derivative of cosine is negative sine, this only works in radians, and I need to know that the area of a circle is pi. So forgiving the pun, this is a bit of a circular argument. Let's assume we know the trig identities and the trig derivatives. So let's just look at this portion of the circle. If I can find the area under this curve and multiply by 4, that will be the area of the circle. So let's try to calculate this. So it's going to be, I want the integral from 0 to 1 of the square root of 1 minus x squared dx. Because this is the curve x squared plus y squared equals 1, so y is the square root of 1 minus x squared. On the bottom half, this is y equals negative square root of 1 minus x squared. So I want to integrate the square root of 1 minus x squared. What function has derivative square root of 1 minus x squared? Saints preserve me, okay? I don't know. But I know sine squared plus cosine squared is 1. So sine squared is 1 minus cosine squared, or cosine squared is 1 minus sine squared. So this suggests we might want to try taking x to be either sine or cosine. And we just have to think about which way do we want to do this. Well, we have x goes from 0 to 1. So if I take x to be sine, it would start off at 0 and go to 1. So that seems like that's a good way to go. So let's try x equals, say, the sine of theta. So as x goes from 0 to 1, theta is going to go from 0 to pi halves. Because when x is 1, then theta is pi halves. So dx d theta, derivative of sine is going to be cosine of theta. So dx is cosine theta d theta. So now we have the integral, theta goes from 0 to pi halves. Again, I like just being very explicit. Square root of 1 minus x squared, that's the square root of 1 minus sine squared of theta. Dx is just cosine theta d theta. Well, what's the square root of 1 minus sine squared? That's just cosine. So this is just the integral from 0 to pi halves of cosine squared of theta d theta. And now the question is, can we do that integral? There's a lot of ways to do this integral. So a lot of this, again, the more math you remember, the easier things are going to be. So we have cosine squared of theta, and we want to know what is its antiderivative. Well, if you remember, cosine of 2 theta is cosine theta minus sine theta, sine theta. This is our trig identities. This is cosine squared of theta minus sine squared of theta. Sine squared, however, is 1 minus cosine squared of theta. So that's now 2 cosine squared of theta minus 1. And that's cosine 2 theta. So cosine squared of theta is going to be 1/2 cosine 2 theta plus 1/2. So if I wanted to then integrate and find the antiderivative of cosine squared of theta d theta, I would need a function whose derivative is 1/2 cosine 2 theta. Well, if I take the function sine of 2 theta, derivative of sine of 2 theta is going to be cosine 2 theta times 2. I want to have a 1/2, right? So I multiply that by 1/4. Now I want a function whose derivative is 1/2. That's just going to be theta over 2. And so now I have an antiderivative for cosine squared. Another way you could do this problem, and this is to use the idea of symmetry. And again, the goal is to just put some things on your radar. The integral from 0 to pi halves of cosine squared of theta d theta, well, with a little bit of inspection, that should be the same as the 1/4 the integral from 0 to 2 pi of cosine squared of theta d theta because of how similar cosine is. But cosine and sine are the same function shifted by 90 degrees. So this should be 1/2 of 1/4 of the integral from 0 to 2 pi of cosine squared theta plus sine squared of theta d theta. Because the integral of sine squared should be the same as the integral of cosine squared. But what does sine squared plus cosine squared equal? 1. So this is the same as 1/8 the integral from 0 to 2 pi of 1 d theta. So that gives me 1/8 of theta evaluated 0 and 2 pi. So I get pi over 4. And this is 1/4 the area of the unit circle. Now, it's not truly impressive because we assumed we knew the area of the circle when we developed sine and cosine, but it's a start. And so this is showing you, the power of trig substitution. So let's do a little bit more interesting problem. So, again, I apologize for the artwork. So with some imagination, here's a sphere. And we want to figure out what is the volume of the sphere. So here, you've got x squared plus y squared plus z squared equals 1. Because we know things are going to scale with the radius. So if I multiply the radius by 2, the volume should increase by 8 because it's a volume. So what we're going to do is we're going to do a slice method. What we can do is we can regard the sphere as a collection of disks. And I'm going to deliberately draw them separated. And for each one of these disks, what we'll have is we will have the thickness, which will be delta x. We'll have the radius, which will be r of x. And in the area will be pi r of x squared delta x. And the idea is by putting them all together, that should give us the volume of the sphere. So if we want to just calculate what's going on for, say, half the sphere, we could send x from 0 to 1. And then for each value of x, we have the volume of that small little disk. And so the total volume is going to be twice the integral x goes from 0 to 1 of pi radius of x squared dx. All right, well, what is the radius of x? Well, we've got to think of what's going on. So here is the x-axis. Here's the circle. Here's the center. Here's our point x. So what do we know? Well, we know that's 1. We know this is x. So r of x has to be the square root of 1 minus x squared by Pythagoras. So now that we know that, this is just twice the integral from 0 to 1, pi square root of 1 minus x squared, and then we squared, oh, life is good. It's just 1 minus x squared dx. So that's going to then be 2 pi. Now, what function has derivative 1 minus x squared? That's going to be x minus x cubed over 3 at 0 and 1. All right, well, when we put in x equals 0, we get 0. When we put in 1, we get 1 minus 1/3. 2/3 times 2 pi is 4/3 pi, which is the volume of a sphere. So we've actually now done something that's worth doing. We went from knowing the volume of a circle, or the area of a circle, to now getting the volume. So the last major theme in Calc 2 is basically Taylor series and convergence. And so we'll just end today talking a little bit about Taylor series, and convergence. So the idea is you're given some function f of x, and you want to approximate by a polynomial. And if the only thing you know about the function is its value at a point, let's say we're doing things at the point 0, I would say f of x is approximately f of 0. If I knew the instantaneous speed, I could say, let's assume we always travel at that speed for all eternity. And I would have f prime of 0 times x. Then let's say, well, maybe we know how the speed is changing. Maybe we know the acceleration. So then we would have, somehow we would want to incorporate that. And the way to do it is f double prime of 0 over 2 factorial x squared. And the next term would be f triple prime of 0 over 3 factorial x cubed. And the reason we put these 2 factorial, 3 factorials is now when you take the derivatives match up. So for example, we can call this the Taylor series of f. And we would get f of 0 is the Taylor series at 0. Well, that's easy to see because every term, when you put in x equals 0, vanishes except for the first term on the right, which is f of 0. Now we can take the derivative. So if you take the derivative of f of 0 is gone. The x squared term is going to give you a 2x that will vanish at 0. The x cubed is going to give you 3x squared that will vanish at 0. The only term that survives is f prime of 0. Well, that's just f prime of 0. So we then get f prime of 0 is the derivative of the Taylor series at 0. And then if you keep going, you would see the second derivative at 0 of our function is equal to the second derivative at 0. So it's designed so that things match up. So whenever you have a series, if there's infinitely many terms, you always have to worry, does it converge? And if it converges, what does it converge to? So the big difference between Calc 3 at Williams is 150 assumes you have not done Taylor series, and we do Taylor series. 151 assumes you have done Taylor series. So given that this is spring and we only offer one section of Calc 3, I will go through and do the Taylor series, but I will say a little bit about some of the big advanced theorems that they do in 151. The main idea is you want to understand when does a series converge? And we'll spend a lot of time in Calc 3, talking about, when does the series converge? So if I give you, the sum, n goes from 0 to infinity of an, this means a0 plus a1 plus a2 plus dot, dot, dot. It is necessary versus sufficient. Have you seen the movie Dodgeball? All right, so one of my favorite lines is when they're talking to their coach. Their coach is a little weird. And he responds at one point by saying, is it necessary for me to drink my own urine? And in shock, the team looks at each other and someone goes, no. And he goes, no, I drink it because it's antiseptic and I like the taste. So we want to understand the difference between a necessary condition and a sufficient condition. A necessary condition, this must happen. So if you want to win the Super Bowl, what is a necessary condition to win the Super Bowl? You're playing in it. If you are not playing in the Super Bowl, you will not win. What is a sufficient condition to win the Super Bowl? You score more points than the other side. By definition, that means you win. So a lot of times there can be conditions that are necessary, but they're not sufficient. So for example, it's necessary that the terms an tend to 0 in absolute value if it converges. If the terms are not tending to 0 in absolute value, that's not enough to, if they don't tend to 0, it can't converge because it's going to go all over the place. It turns out it's not sufficient. So an going to 0 is not sufficient. So for example, the sum of 1 over n squared converges, but the sum of 1 over n diverges. And so we develop a lot of very detailed tests in Calc 3 to determine when a series converges or diverges. The last thing I guess I should just briefly mention is differential equations. And we'll end at that. So in Massachusetts, we are now doing physics in 9th grade before students have even done algebra 2 in many cases. And because this is being recorded, I will leave it at that. So Newton's famous law is F equals ma. And so acceleration is the derivative of the velocity, and velocity is the derivative of the displacement. And so one of the things we try to do is, if I give you one curve, can we find the other? Well, so for example, since velocity is the derivative of the distance, if I integrate the velocity from, say, A to B, then that's going to just be the integral from A to B of x prime of t dt. That's going to be x of b minus x of a. So we can use this to develop all the different kinematics equations that you would see in classical physics. And if we know calculus, we can do this. What we often want to do is we want to solve differential equations. So we want to solve, for instance, maybe we tell you y prime of x is equal to x plus e to the x. Can we find y of x? And maybe I'll give you some initial conditions. Y of 0 is 2. And the goal is to try to figure out how to solve something like this. And so again, the more I know about a function, hopefully the more I should be able to say. And if I know my speed at every moment in time, the hope is that that would uniquely determine where things are. The problem is a lot of things that seem true turn out to be false. And you have to be very careful. So the following function is one of the most evil functions in the universe. It is e to the negative 1 over x squared if x is not 0, and 0 if x is 0. So if you were to plot this function, if you were to plot this function is extremely flat near 0. If you think about it, if you take x equals 1 over 100, this is e to the negative 100 squared. If you take x equals 1 over a million, this is e to the negative a million squared. This function is of extreme rapid decay. It turns out, if you try to calculate the derivative at 0, well, we can't just take the derivative because it has a split definition. So you have to go back to the definition of the derivative. Turns out you use L'Hopital's rule, and you get all of its derivatives as 0. So if you try to calculate the Taylor series would be identically 0. This should not be allowed to happen. The function is nice, the function is differentiable, we can compute all the derivatives, but the function does not converge to the Taylor series, except the Taylor series does not converge to the function, except at the origin, where this is a really, a no shit Sherlock moment, because, well, if you look at how we define things, we define the Taylor series to be f of 0 plus things that are 0 at 0. So the function has to equal the Taylor series at 0 by definition. But what this is showing us is for this one special case, that is the only point where the two are equal. So the Taylor series converges, but it does not converge to the original function. This is why we have more advanced math classes to worry about situations like this. You would think, well, if my function is differentiable, if all the derivatives exist, build the Taylor series and the Taylor series will converge to the function. Sadly, not necessarily. Although at least in this case, the function is so small that it is going to be very close to it, but it's not going to be converging to it. Right? Any questions of things you wanted to see from Calc 2 that I did not cover? There's a lot of material. All right, so I'm going to stop the recording.